Alrighty, class. So looks like we are going to go over a new unit. This is actually unit 7. Why I have that unit written up? But this is unit 7. We're going to be talking about parallelograms, or sorry, quadrilaterals. But we'll talk about parallelograms, quadrilaterals, and other polygons. Okay, so the first lesson for today is 7.1, 7.2, which you'll find in your notes. And the first key point we're going to go over is the interior angle measures of polygons. Okay, in a polygon, two vertices that are endpoints of the same side are called consecutive. Oops, can't spell consecutive. Consecutive. There we go. Vertices. Okay. Then a diagonal of a polygon is a segment that joins two non-consecutive sides. Okay, or non-consecutive vertices. Okay, so two things really. Some new key vocabulary that is going to seem like a word that we've heard before, and we have heard these words before, but I kind of want to just reiterate them. Non-consecutive and consecutive. Consecutive means basically back-to-back. Then non-consecutive means not back-to-back, right? So non means not, or non, or no, not back-to-back. Okay, so not back-to-back. And so as we can see in the diagrams, of the diagonals from one vertex to divide a polygon into triangles, right? We can see it on this right-hand side. Dividing a polygon with insides into n minus 2 triangles shows that the sum of the measures of the interior angles of a polygon is a multiple of 180 degrees. And that is definitely one of our more important things to get out of this. And so, using the diagram here, we can clearly identify what is a consecutive and what is a non-consecutive. Right? You see A and B here. Those are going to be consecutive because they're back-to-back vertices. Whereas B and E, on the other hand, is going to be non-consecutive because they skip over one and they're not directly touching each other in the figure. Okay. Don't get fooled by these red lines here. Oops. Don't get fooled by these red lines here. They're just indicating that there exists a diagonal, not that they are connected at all. Okay. Theorem 7.1, the polygon interior angles theorem. All this rigmarole, right? All that stuff is basically just giving us this equation, or rather this expression. And this expression, n minus 2 times 180 degrees, gives us degree measures of polygons. Okay. And so basically, all we have to do is just count the sides. N, of course, is the number of sides. And so as long as we know what the number of sides are, or if we know how many degrees we equal, then we're going to be able to use this equation. So looking at the example that's given to us in theorem 7.1, right? We have to make our triangles. One diagonal there, another diagonal here, and then a last diagonal there. Notice that we have a 6-sided figure, so n equals 6, but we have 4 triangles that are created. And since each triangle equals 180 degrees, it's basically saying that 4 times 180 degrees equals the amount for our 6-sided figure here. Okay. And that's the idea that we're going to run with. Okay. So if you actually did all that math, you'd get 720 degrees, meaning a 6-sided figure will be 720 degrees in the inside. So we move on. We keep this understanding in our mind and move on. to our first couple of examples. And so we look at this example here, and we're told that we're supposed to find the sum of the measures of the interior angles of the figure to the right. Okay, well, first let's count the sides. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, if it's helpful, you can draw all the triangles if you'd like. Yeah, I'm not going to, but if you'd like to, you can. And so because we have n equals 8, then we're going to plug that into our equation. So 8 minus 2 times 180 equals some degree measure. We don't know. But we'll do that math. We get 6 times 180. And that's going to give us 1080 for our degree measure. Okay. Because this is or rather an 8-sided figure, this is what we call an octagon. Octagon. Okay. I suggest moving to the next problem and doing it on your own first, then check back. Find the sum of the measures of the interior angles of the figure on the right-hand side again. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have n equals 10. Again, just plug that right in for the equation. We get 8 times 180, which then equals 40 degrees. And just so that we're aware of what this figure is called, if a figure has 10 sides, this is what we call a decagon. A decagon. Move on. Now, example 2 is very similar to examples 1 and extra example 1. Very similar. Okay, but instead we're looking for the number of sides. So we don't actually have the number of sides yet. We do know what the polygon equals. So set up our equation, n minus 2 times 180 equals 900. And you're just going to solve for n, just like how you would solve for any other variable. Divide by 180 on both sides. N minus 2 equals 5. Then you add 2 on both sides, we get n equals 7. And it does say to classify the polygon. I don't imagine a lot of us know how to classify polygons, or at least by their names. But for a 7-sided figure, this is what we call a heptagon. A heptagon. Again, take some time to do that extra example 2. But we're still going to look at it regardless. This is the exact same problem as example 2, just with some different numbers. So n minus 2, 80, equals 1800. And then I'm getting a little skittish over here, or getting a little ahead of myself. Divide by 180 on both sides, we get n minus 2 equals 10 plus 2 on both sides, n equals 12. And this figure is what we call a dodecagon. Very fun. Dodecagon. Okay. Simple. Then we have a corollary here. The corollary is not really that important. I mean, yeah, quadrilaterals equals 360 degrees, but I think a lot of us already knew that. And I don't really think it needs to be its own corollary. That's just me. But, you know, we had the theorem for a reason, and the corollaries are based off the theorems. So may as well just have it. But then for this problem, again, this is actually a really simple problem. For example, 3. We have an announcement from our. Oh, you know, today is, or this week is our spirit week. So we're looking to figure out who has the most spirit of our high school students, which which grade level has the highest spirit. So we'll see. For Mr. Mouth here, as you can tell. Here we have example 3. Find the value of x in the diagram. We know that this is some sided figure. Let's see. Let's count 1, 2, 3, and 4. So it's a quadrilateral, which we said quadrilaterals are 360 degrees. And we're looking for the value of x degrees. But we know 108 plus 121 plus 59 plus x is going to equal 360 degrees. So you add them all up, you get 288 plus x equal 360. Subtract both sides by 288, you get x equals 72 degrees. Okay. That's usually pretty simple, nothing too hard. Now for key point 2, however, this is where it gets a little bit trickier. Okay. Beforehand, when we talk about triangles, we always said that the equilateral triangle was also equiangular. Okay. This, however, is very different. Okay. A quadrilateral, all sides, or sorry, equilateral polygon is going to be all sides are congruent, which are indicated by all the hash marks. Yes. So sides congruent. That's for equilateral, which again, not a new vocabulary term, but something to distinguish. Equiangular has all the angles congruent. So angles congruent, that's equiangular. But then we have a concept called a regular polygon, where both are true at the same time. So sides and angles are congruent. This is called what we call regular. Okay. Here, I want to make the very clear distinction is that these are all very different. Okay, each one is distinctly its own, and you really should not try to mess around with both, with all at the same time. Okay, equilateral and equiangular are very different, as you can see. Look at all these angle measures for the equilateral polygon. There are some acute angles and there's some obtuse angles. So therefore, it's not going to be equiangular. But then for the equiangular polygon, it's clear that we have all equal angles, but it's very clear to us as well that there's not a congruent side. Or sorry, there's not all congruent sides because that top and bottom side are longer than the other ones. But then our regular polygon creates the best of both worlds here, and we have everything very good, very nice neat. Okay. Then we move on to example 4. We employ that idea of regular polygon and equilateral and equiangular, and we look at this baseball field here. Okay, a home plate, or sorry, we're looking at a home plate. A home plate for a baseball field is shown. A is the polygon regular, explain your reasoning. And B, find the measures of angle C and angle E. Well, remember, what it means to be regular means to have congruent sides and angles. It doesn't tell me anything about my sides, so it's kind of up in the air whether or not I can confirm that for sure. But if we look at our angles, notice that angle A, B, and D are both, or sorry, not both, all 90-degree angles. And E and C seem to be some sort of obtuse angle. So because we don't have all congruent angles for sure, because again, we don't know about sides, because we don't know for sure that angles are all congruent, then this is not a regular polygon. So your answer could be somewhere in the ballpark of the polygon is not regular because you can say something like angle C is not congruent to angle A, for instance. Where it's very clear which angle we're talking about. Then for B is where it gets a little bit trickier, only because there's a little bit more math involved. Okay, it says we have to find the measures of angle C and angle E. Well, I don't know about you, right? I can't tell you off the top of my head what a pentagon interior angles add up to, so we have to figure that out. But we know this is a pentagon because it's 1, 2, 3, 4, and 5 sided, and it has 5 angles. Okay, 5 angles, 5 sides means pentagon. So I have 5 for my number of sides, and minus 2 times 180. And you do all that math, and you get 540 degrees. Well, I don't know what E and C are. That's what I'm trying to look for. But I do know what A, B, and D are because they're all right angles. So I'm going to take 540. I'm going to subtract 3 right angles. So I'm going to say 90 times 3. PIMDAS, okay, order of operations says to do the multiplication first, then addition and subtraction. So multiply first, then subtract. When we do that, we are going to get 270. And because I'm looking for 2 angles that say that they're the exact same angle measure, just divide by 2. Which then equals 135, which means that angle C, or the measurement of angle C, equals the measurement of angle E, which is equal to 135 degrees. Pretty simple. I don't believe you have an extra example 4, but it's very much the same. Okay, this example 4 here, you can see very clearly that a lot of these angles are not the same, so it's not regular. Okay, for the exact same reasoning as above. And then you'll find your angle measures by doing the exact same process. Figure out step 1, I suppose you could say, is figure out how many degrees are in the inside. Then step 2, subtract your known angles. And then step 3, figure out what the missing angle is. So if you wanted to put it in steps, you could do it like that. Highly recommend you do it on your own time, though. Key point 3, a parallelogram is a quadrilateral with both pairs of opposite sides parallel. And you can read this figure, the little symbol there, as a parallelogram or as a quadrilateral. Typically, it's because it's specifically saying about parallelogram, you might want to just call it parallelogram. And I just realized I also spelled parallelogram wrong. There we go. In parallelogram, there we go. PQRS. Segment PQ is parallel with RS, segment RS, and segment QR is parallel with segment PS by definition. The theorems below describe other properties of parallelograms. Okay, so far, so good. I think, the diagram shows it to us very nicely. QR is parallel with PS. And then additionally with QP and RS. Okay, so those are the pair of opposite sides that are parallel. Okay. But then we look at these next 2 theorems, the parallelogram opposite sides theorem. If PQRS is a parallelogram, then PQ is parallel or is congruent with RS, and QR is congruent with SP. Okay, so we got to break this down first, right? The first thing I would really do is actually go back to the little sentence that we just got. So go back to that sentence. And what we're going to say is that the definition of parallelogram, we'll just draw ourselves a little parallelogram, is 2 pairs of opposites parallel lines, parallel sides, I guess you could say. Okay. But then we look at 7.3 and it's also saying that those two pairs of opposite parallel sides are also congruent. So now we have two pairs of opposite congruent sides. Not sure why that erased. Congruent sides, there we go. And that's basically what 7.3 or 7.3 is telling us. But then 7.4 says basically the same thing, where if PQRS is a parallelogram, then angles are going to be congruent. But you got to be careful, it's going to be opposite angles. Okay. So we're going to still run with this theme of two pairs of opposite congruent angles. Okay. And this is true for all parallelograms. Okay. If it can be classified as a parallelogram, then every single parallelogram is exactly like this. Every single one. Okay. We'll learn later what classifies as a parallelogram. And actually, you have a nice handy worksheet, and well, not a worksheet, a table that shows all the criteria of each of the shapes that we're going to be going over in this unit. I will not go over that for this lesson, only because it's a lot of time to get into that stuff. And whenever I can just post you the key. So I'm just going to post the key on Schoology for us, and we'll be fine. But this is what we're looking at. Then, for example 5. Example 5 is going to employ what we just learned and put into action. So if I look at this problem, I know this is a parallelogram because of the two pairs of parallel sides. Well, if I know I have two pairs of opposite parallel sides, then I know that I'm going to have two pairs of opposite congruent angles and sides as well. So because I know all this, because this is all a parallelogram, I'm going to label it as such. So I know AB is congruent with DC, and I know AD is parallel with DC. So I'm going to make sure that I mark that with some congruent signs because they're congruent now. We just said. But then also with our angles, angle C is going to be congruent with angle A because they're opposite angles. Angle D with angle B. Okay, just be very careful, right? Don't do the mistake I almost made. Okay, those are going to be two different pairs of congruent angles. Two distinctly different ones. And so what we're going to do, I already have the purple color out, so let's look for our angle for our y. So because we know that angle C is congruent to angle A, we can say that the measure of angle C is equal to the measure of angle A. Oops. Because they're equal to each other, substitute what they mean, or what is in our problem here. 65 is the measure of angle C, and the measure of angle A is y degrees, which means that y must be 65. Pretty simple. Pretty simple. Then we have our sides, where I said that AB is congruent with DC, which means that AB equals DC. I'm going to do the exact same thing. AB is x plus 4, BC is 12, subtract 4 on both sides, get x equals 8. And that's my answer. Pretty cut and simple. Nothing too difficult for us. Okay. And even then, you don't have to do the first two rows. I'm just showing exactly why we're able to say this. But if you can go straight into saying that 65 equals y, go ahead. If you can go ahead and if you can straight away say x plus 4 equals 12, go ahead, do that. Okay. I'm just labeling all the steps or labeling how I got from which way. In essence, this is basically a proof without reasons, other than me verbally telling you what the reasons are. Example 5, do on your own first, and then try with us. I know that these are all congruent, or sorry, not all congruent. I'm going to be careful with my words. I should be more careful with my words, but I'm not working off a script here. I'm just working off of what the problem shows me. Okay, I know that these are parallel sides because of these triangles here. So parallel, parallel, and two pairs of opposite parallel sides. That just means that we're working with a parallelogram. So let's label it as such. PS has got to be congruent to QR. PQ has got to be parallel or congruent. Man, I keep getting those words mixed up. I keep meaning to say congruent. Okay, PQ is congruent with RS. Okay, so let's go ahead and solve for our sides then. We know that 3y minus 1 is equal to 20 because PQ equals RS, right? Again, I'm just going to go ahead and skip those steps. So we get 3y on one side, add 1 on both sides, we get 21. Divide by 3, y equals 7. Pretty simple. Now time for our angles. We know P and R are going to be congruent, and we know S and Q are going to be, because they're opposite angles from each other. So 2x equals 54. Divide by 2 on both sides, we're going to get 27 as our answer. And that's pretty much it. We do have 2 more examples to get through, so we have 1 more key point and 1 more example here. And so we look at key point 4, the consecutive interior angles theorem that we learned back in Unit 3. States that if 2 parallel lines are cut by a transversal, the pairs of consecutive interior angles formed are supplementary. Okay, coming back to that Unit 1, Unit 3 stuff, supplementary. Okay. So now that we have this idea for us, we've got this idea of supplementary. We're going to see it in our theorem here, 7.5. And again, basically what we're saying here is what it says in the actual if-then statement. That if we have 2 angles, we're going to probably equal 180 degrees. So where beforehand we said opposite, I'm going to abbreviate opposite with opposite angles are congruent. We're going to say consecutive angles are supplementary. And that really makes sense, right? We know that the actual quadrilateral, the parallelogram, equals 360 degrees. But what we also know is 2 of them are going to be, or 2 pairs of them are going to be congruent to each other. Well, if I divide up 360, that equals 180. And so, because I'm able to make this distinction, half my angles should add up to 180 degrees. In my mind, that makes sense. Okay, if what I just said made you a little bit more confused, you can ask me questions, of course. Okay, maybe I didn't explain it as well as I wanted to. But that's what we have for theorem 7.5. And then for parallelogram diagonals theorem, something that I want to write in here is that I don't think the if-then statement does quite enough justice to it. What I would write is for this theorem is diagonals will bisect each other. Okay, diagonals will bisect each other. I think that's the best way to explain it. Remember, to bisect something means to cut into 2 congruent pieces. Well, if the diagonals are going to directly bisect each other, it's directly cutting them in half. That's why we see PM is congruent to MR and QM is congruent to MS. Okay, in my mind, again, it just makes sense to me. But this is going to be a theorem that we're going to probably revisit later in the next the next section because we do have some proofs to do. And of course, everybody loves proofs. So that's what we'll do. We have example 6 here. If, okay, I know on your notes it's going to be a little bit harder to see because of that black and white. If you can't see the parallelogram, redraw it. Okay, redraw it to look something like this. Make it still look somewhat similar to how the orientation is on the actual diagram is. So that's why I have it at an angle rather than on a flat surface, because it makes more sense like doing it this way. So we'll have it A, B, C, and D. And that's just the pre-work, right? Just redrawing the diagram so that we can actually read it. Okay, example 6. As shown, part of the extending arm of the desk lamp is a parallelogram. The angles of the parallelogram change as the lamp is raised and lowered. Find BCD. I'm not quite sure why they wanted to say BCD whenever they could have just said angle C, but that's just me. So we're looking for this angle. When we know that the measure of ADC, again, I don't know why they didn't say angle D, is equal to 110 degrees. So we know that this angle, ADC, is 110 degrees. And now there's two ways to solve for this. One is the longer way, and then the second one is the shorter way. The longer way will take us, well, I know angle D is 110 degrees, which means angle B is also 110 degrees. Right? That just makes sense because they're opposite angles from each other. So 110 degrees. But then because I know that this is a parallelogram still, right? Angle C means that angle A is going to be the same measure, but we don't know what angle A is. And so we would add D and B, subtract that from 360, and then get that number and divide it by 2 and figure out what angle C is. That sounds like a lot of work. I don't think anybody has time for it or nor wants to do. So instead, we're going to use that theorem 7.5 to our advantage. If we know that opposite angles, the ones that do not touch each other, opposite angles, are congruent, we said that the consecutive angles are supplementary. So if D and C are consecutive, which they are, then that means that they're going to be equal to 180 degrees. So we'll write measure of angle D plus the measure of angle C equals 180. We know the measure of angle D, which is 110, plus the measurement of angle C equals 180. Therefore, measure of angle C is 180 minus 110, which is 70 degrees. And that's pretty good. Pretty simple. Okay. We don't have an extra example 6. But I do kind of want to illustrate how to solve this one. Only because I think a lot of us might find this a little bit confusing just given the wording. It says parallelogram PQRS. Oop, strike through it. PQRS. Measurement of angle P is 4 times the amount of measurement of angle Q. Those are both very important pieces. Find measurement of angle P, draw yourself a picture if you are stuck. And I really do suggest drawing a picture, right? So let's just draw our parallelogram like so. But you want to be careful here, okay? It doesn't give us PQRS just to give it to us. We have to follow that order. So if I say that this is P, then this is Q, then R, then S. Okay, you can't say that Q is actually the opposite angle to P. Okay, that just doesn't make sense. You can't do that. So what we do from here is we figure out, well, I know P is this angle, and I know it's 4 times the measure of angle Q. Angle Q we'll just call X for now, X degrees. But angle P is 4 times as large, so it's actually going to be 4 times X degrees. Then, because we know that consecutive angles are going to be supplementary, add them up. Put them equal to 180, 5x, 80, which if we get our x value, x equals 36. Good. Now that I know my x value, I can say, well, the measurement of angle P is equal to 4 times x, which is 36 now. Therefore, the measurement of angle P is equal to 100 4 degrees. Okay. Like I said, pretty simple. For example 7, I want us to map out those 3 vertices. So -1, -3, right here. That's W. 3 or -3 and 2, right here. That's X, and Z is 4, -4, which is right here. And we'll go ahead and connect them. Okay. And it tells us to find the coordinates of vertex Y. Well, that's an interesting question. I don't think we've seen something like this before. At least nothing from recent memory. But part of me is thinking, well, I know it's a parallelogram. Okay, let's think about all the things that are true about parallelograms. They have 2 pairs of parallel sides. They have 2 pairs of congruent sides. They have 2 pairs of angles. 2 pairs of congruent angles. But which one is actually going to help me here? I can definitely find the distance with the coordinate grid because I can just use distance formula or Pythagorean theorem. That could be easy enough. Can't really find angles though. I don't have a protractor, so it's not going to help me here. But the one that's going to be most helpful is actually going to be our parallel sides. Remember, on a coordinate grid, parallel means to have the exact same slope. So if we were to take the slope of xw, we will be able to find the opposite side's slope as well. And so in essence, right, we have a parallelogram that looks supposed to be like this, where we have x, w, and z. We have some unknown y value or unknown y coordinate. We don't know what y is, but we know it's somewhere going to be in that region. Because if we go backwards, that's not going to be a quadrilateral. That's not going to make sense, or at least not a quadrilateral that we want to work with. And so we have to figure out what these slopes are. Okay. Well, let's look at wx or xw, however you want to say it. Let's find the rise of a run of it. So if we took our rise from x to w, we went 1, 2, 3, 4, 5 units down, which means that our rise is actually -5 units because we're going downwards. So this is for xw slope. And then we went 1, 2 over. And now because we know that this is for the y side, right, the side with the y, we have to go backwards from there. So if we look at z, we're going to go backwards. We're going to go up 5 units. 1, 2, 3, 4, 5. And then to the left 2 units. 1, 2. Which means that our angle, or sorry, not our angle, our vertex y is going to be that point right there. But if that doesn't make sense to you, or if you're skeptical of that being the answer, then do it the other way around as well. What I mean by that is find the slope of wz, then you can find the slope of xy. So if the slope of wz, right, I'm going to find my rise over run. I went down 1 unit, so we already have a -1. Then 1, 2, 3, 4, 5 units to the right. And so I'm going to work not necessarily backwards like we did with z, but we're going to work from left to right with our x value. Right? We know that x is supposed to be the left side of that side xy. So we'll go down 1 unit, then over 5. 1, 2, 3, 4. And would you look at that? That makes so much more sense now. So if I were to erase all this extra stuff, all that extra stuff, try not to get everything else taken out, we should have a parallelogram that looks like this. All of that without really even doing any math, all I did was count. Okay. So when you see this on your next quiz, and you will see this on your next quiz, I would just count it. Okay, just count it. It's going to be a heck of a lot easier than trying to figure out, oh, what's the distance formula and Pythagorean theorem and trying to find those angle measures. No, No, don't do all that. There's no need. Okay, don't do all that. Don't do more work than you need to. Just count it. Okay. But realize you are counting the slope and not counting just random numbers. Okay. So that concludes this lesson for today. That is 7.1 and 7.2. If you have any questions, of course, you can message me if you need to. You can ask any questions so long as they're appropriate for the class, or you can message me at some other point. Okay. So now that we're done here, I will talk to you all later. All right. Goodbye.